So good evening all. Welcome to this tutorial session 5. Today we will discuss the review of week 5 lectures. We will briefly recap what has been covered in week 5 lectures and the problem related to deflection of beams and frames. Today we will mainly focus on two methods. One is conjugate beam method and another one is unit load method. So first we will see what this first method, that is conjugate beam method, says. So the first method for today's class is conjugate beam method. As the name suggests, conjugate beam. Conjugate beam means it is only applicable to beam structure. You cannot apply this method to any other structure apart from beam. So the name suggests it is applicable to beam only. And conjugate means you need to find a beam equivalent to the real beam, which is called as a conjugate beam, such that some of the parameters, like if this is the real beam, and let us say this is the conjugate beam. I don't know now, there might be some other support, but for simplicity now I am showing it hinge and roller only. But I don't know if for this real beam like this, the conjugate beam will be like this or not. But for the sake of simplicity, let us now consider the conjugate beam is like this only. Now, in this method, the main question will be like this. We need to find either deflection or rotation, or which is also called as slope, at a certain point. Within the span. So we will make a conjugate beam. There, this slope and deflection can be correlated with some other parameters which are called as kinematic parameters. When you will find all these parameters, this indirectly will give the deflection and slope for the real beam. So for this, we have two theorems. One to determine slope and another to determine deflection. So the first theorem states that the slope at a point in the real beam is numerically equal to shear force at the corresponding point in the conjugate beam. Like we know dV by dx will be equal to W. We also know d theta by dx will be equal to M by EI. So when you will integrate it once, it will give shear force equal to W dx integration. And here theta will be given by M by EI dx integration. So now you can correlate how this shear force is related to slope. Here it is W, here it is M by EI. So now, if you have a real beam like this, and the loading is suppose UDL. For this, the bending moment diagram will come out to be parabolic like this, and this should be positive. Now this is M, so you can do M means divide all the ordinate by EI, that is normalizing by flexural rigidity, you will get the M by EI diagram. Now for this real beam, when you will draw the conjugate beam, we will see how to draw conjugate beams by changing the supports and all in the subsequent slides. Now I am, for simplicity, I am considering this as the conjugate beam for this real beam. Now take this M by EI loading and make this act as a load in this conjugate beam. Now from these two equations 1 and 2, when you will compare, we have changed our load W to M by EI such that for real beam, wherever we are interested in calculating the slope, if we will go to the conjugate beam, and at that point only if we will calculate, suppose at midspan here, we need to calculate the deflection. Now come to conjugate beam, come to the midspan, let us name it as C, come to point C, apply the M by EI diagram. This is M by EI diagram as loading for this conjugate beam. Come to point C, and in this point C, you calculate shear force, and that will give you theta or slope at that point for real beam. Similarly, to calculate deflection, so the theorem states that the displacement of a point in the real beam is numerically equal to the moment M at the corresponding point in the conjugate beam. Suppose, consider this example only. This is a simply supported beam and UDL is there. Now the BMD comes out to be like this. Take the BMD or M by EI diagram to the conjugate beam, and let us suppose we have to find the deflection at point C. Now you come to that point C in the conjugate beam, find the bending moment diagram, find the bending moment at point C, and that will correspond to the deflection delta C for real beam. So in short, if we want to summarize, first we need to convert this real beam into a conjugate beam by taking all those support conditions into consideration. Then for real beam, we need to draw the M by EI diagram. Take the M by EI diagram and place it on the conjugate beam. Determine all the support reactions if needed. Then move to that point where we are interested in finding the slope or deflection in the real beam, and in the conjugate beam you determine the shear force or bending moment at that point, and that point will give the slope and deflection for the corresponding real beam. Hope this is clear.
Yes, sir.
Yeah. Shall I proceed?
Yes, sir.
Now, these are some of the real beams. Now let us draw the conjugate part of those beams. Now, in the previous slide, we got that slope and deflection of real beam will be equal to shear force and bending moment of conjugate beam. So these are all real beams. Now, when this is hinge support, so here what will be theta and what will be delta? Here delta will be equal to 0 and theta we don't know the value, but it won't be 0 because when loads are applied, the deflected shape, if the loads are applied downward only, I am assuming, the deflected shape will be like this. This point is neither moving in horizontal direction nor moving in vertical direction. And that's the property of a hinge. But here when you will find there is some slope. So theta is not equal to 0, but displacement or deflection at this point delta equal to 0. Similarly, for roller also theta won't be equal to 0, as you can find it here. There is some slope and delta equal to 0 because there won't be any translation. Now, when we will draw the conjugate beam, we have stated that theta of real beam will be equal to shear force of the conjugate beam at that point. So let us draw. Here theta should not be equal to 0 and delta should be equal to 0. So what kind of support will provide that condition in conjugate beam such that our shear force, let shear force be given by V and bending moment suppose PM, such that our shear force won't be 0, but bending moment will be equal to 0. Similarly, here also our shear force should not be equal to 0 and bending moment will be equal to 0. So, what kind of support we can give such that it will satisfy these two conditions? Anyone?
Hinge support.
Sorry, which kind of support?
Hinge.
Hinge support. Yeah, correct. If we will provide hinge support, see, there won't be any translation. And if loads are applied, reaction will come. So at this point, shear force will be present. But at hinge, will it will it carry any bending moment or it is free to rotate? It is obviously it is free to rotate. So bending moment will be 0. So from these two conditions are satisfied when we are considering it a hinge. Now come to this part. Same two condition needs to be fulfilled and this can be done with either a hinge or a roller. Now come to this beam, cantilever beam. Now see here, theta will be equal to 0 because when loads are coming, the deflected shape will be something like this. So theta is also 0, delta is also 0. But here when you will see, there will be some slope. So here theta won't be 0, delta won't be 0. So for this, we have to determine supports at these two conditions such that here shear force becomes 0 and bending moment becomes 0, and here shear force and bending moment should not be equal to 0. So here, as shear force is 0, so there is no restraint against vertical movement, and bending moment is also 0. So it can also rotate. So if we keep this point as free, then both these conditions will be satisfied. Is it or no?
Yes, sir.
Yeah. Now come to this joint. Here shear force also should not be 0 and bending moment also should not be 0. So if we are making it fixed under some loading, that is M by EI loading of the real beam, we'll get some shear force here, and when under this loading, when it try to bend, there will be some bending moment. So this is the corresponding conjugate beam for this cantilever beam, which is real in nature. Now come to this third real beam. Now I am drawing it quickly. Here it is hinge. So there will be some rotation or slope, and there won't be any displacement. Here, when you will see, there will be some slope. There will be some slope, but the displacement delta won't be there. When you will come to this, both theta and delta should not be 0. So when you will satisfy for conjugate beam, it should be VF should not be equal to 0 and bending moment can be 0. So directly put a hinge support here. Here see, here for conjugate beam at this point, suppose our shear force should not be 0, but bending moment can be 0. Here and when we are coming to this point, here both theta is not 0 and delta is also not 0. So our shear force won't be 0 and bending moment also won't be 0. So it is the same case like this. So it will be fixed. And now let us think about this case. Here shear force won't be 0, but bending moment will be 0. So can we insert at this point a bending release or a internal hinge? Will this do?
Sir.
Yeah. So come to this fourth and fifth. Let us first draw for fourth and then fifth. Fourth, here, now see. Here theta will be 0, delta will be 0. So you can make it free. Here it is internal hinge. So you can make it as roller, which is internal roller. Here it is roller only. So let it be roller. So this is the conjugate beam for this structure. Here you know that what you can see. Theta won't be 0, but delta will be 0. Here, when you will do this, delta won't be 0 and theta also won't be 0. So from this, when you will satisfy, here you will see shear force and bending moment, both are 0. Here, there will be some shear force, so shear force can't be 0 and bending moment also can't be 0. And here also, shear force can't be 0, but bending moment will be 0. Now come to this last one. Fixed will become free and internal roller will become internal hinge and internal hinge will become internal roller and this hinge will remain as it is. So is this clear to all of you?
Yes, sir.
Yeah. Can you tell what will be the theta and delta here? Will it be equal to 0 or not equal to 0?
Not equal to 0, sir.
Yeah, here
Not equal to 0, equal to 0.
what theta not equal to 0 and delta equal to 0. Correct?
Correct.
Yeah. And here in internal hinge,
Theta is not equal to 0, delta is not equal to 0.
yeah, here
Theta is not equal to 0, delta is equal to 0.
come to this. Let us check the consistency. Here shear force and bending moment.
0, sir.
Yeah. So are they consistent now from here and here?
Yes, sir.
Come to this point. What about shear force and bending moment? Tell me quickly.
Shear force is not equal to 0, bending moment equal to 0.
Here,
Shear force is not equal to 0, bending moment equal to 0.
how come it become equal to 0?
Not equal to 0, sir. Internal.
It is internal roller.
Internal.
Yeah. Now here,
Shear force is not equal to 0, bending moment equal to 0.
yeah. Now check the consistency. Are they matching?
Yes, sir. Matchings.
Yeah. So I am proceeding further. Now let us solve this problem. Here they are asking to determine the deflection at point B. Point B is this internal hinge. Shown below using conjugate beam method. EI is given as constant throughout. So for this beam, let us first draw the conjugate beam. I am drawing it first. You will tell if I have done it correctly or not. Say if it is correct or not.
Correct, sir.
This is the conjugate beam I have drawn. Now, the second step is step 1 is to determine the bending moment diagram for the real beam under given loading condition. Now, when we will draw the FBD of this complete structure, this is a fixed support. So, AY, the vertical reaction will come and with a movement. Let the movement be MA. This is internal hinge. So, here bending moment will be equal to 0. Here this is a roller. So we will get one reaction vertical, that is Cy. Now let us apply the equations of static equilibrium. I am dividing this beam into two parts from this internal hinge. So now I am considering the right part. Here this is Cy. Loading is there throughout the span. This is 20 kilonewton per meter. This is 2 meter. This is 2 meter. What else? Here this is B. This is D. 2 meter, 2 meter done. Yeah. Now, here bending moment is 0. So I am directly writing it as 0. Now, the shear force. What is the positive direction of shear force here? Will it be upward or downward?
Upward.
Yeah. So let this be By. Now, when you will take summation of movement about point B of I equal to 0 from right hand side, what we will get? And I am taking clockwise to be positive. So minus Cy into 2 plus 20 into 4 into 4 by 2 will be equal to 0. So from here Cy will be 2 160 by 2, or directly we can write 80 kilonewton. So Cy we got as 80 kilonewton. Now for the entire structure, we can write summation of force along y direction equal to 0, and vertically upward I am considering it to be positive. So we will get Ay plus Cy will be equal to 20 into the total length, that is span length 6 meter. So from here, when we will put Cy to be 80, we will get 160. So from here, we are getting Ay to be 160 minus 80. 160 minus 80 will be 40 kilonewton. So AY is also 40 kilonewton, that too in upward direction. Now, this movement we need to determine. Now, we can do summation of movement. Let us write it here. Summation of movement about point A of I equal to 0. Let us take clockwise to be positive. So if we will do this, we will get minus Cy into 4 plus 20 into 6 into lever arm will be 6 by 2, that will be 3 plus MA equal to 0. Now we know the value of Cy as 80. So it will be, when we will put here as 80, it will be minus 320 plus this will be 360 plus MA will be equal to 0. So from here we will get MA as minus 360 plus 320. So minus 40 kilonewton meter. So what does this minus representing?
Anti-clockwise movement.
Yeah, we have assumed it to be clockwise, but it is coming out to be negative. So the direction should be opposite, that is anti-clockwise. So now to add some slide. Yeah. So now let us show all the reaction forces. This is 40. Here somewhere this is A point. This is 40 kilonewton meter. This is point B. This is CY as 80 kilonewton, and throughout the beam we have 20 kilonewton per meter. So let us draw the bending moment diagram. Now, let us take a section here and cut it out. Let this section be MAA. So I am showing this section from left side, which is at a distance of X from the left support. So we have 40 kilonewton here. This section is cut out. This will be 40 kilonewton meter. And this is the UDL 20 kilonewton per meter at a distance of X. So the bending moment here will be shown as MXX, and shear force here. Which direction will be taken such that our positive notion will be there? Upward or downward?
Downwards.
Yeah. VXX. Now, let us directly write MXX because we don't need VXX now. So MXX will be equal to 40 into X minus 40 minus 20 into X by 2. So it will be 40X minus 40 minus 20x square by 2. So rearranging will be minus 10x square plus 40x minus 40. So this is a 2-degree parabola equation. So here at x equal to 0, we are getting mxx will be equal to minus 40. At x equal to 2 meter. This is 2 meter, this is 2 meter, this is 2 meter. So at x equal to 2 meter, we are getting mxx as 0. And it is obvious there is bending release, so bending moment at point B should be 0. Now, there are two possibilities. Either the bending moment diagram will be like this, or it will be like this. So which one is correct? This is one first, this is second. One is correct or two is correct? Speak out.
Please explain, sir. I have a little bit confusion in this diagram.
Yeah, means how to draw the bending moment diagram when parabolic case is there, correct?
Yes, sir.
Yeah. Okay. Now, in the when we are discussing those bending moment diagram in week 2, I guess, we came across all those differential equation. That is dm by dx will be equal to v. dv by dx will be equal to minus w.
Double.
And what else? These two equations only. No. See, means for simplified case I am showing, and you can do it for all other cases. Let us talk for UDL case only. UDL is there in simply supported way. So you can directly tell from the concept of slope only. We have to do SFD here and we have to do BMD below that. So this is W per meter. Now, this minus W is coming for this case. Means I have taken a small element from here. Let this be dx. This is W per meter. So here it will be V. Here it will be V plus dV. And here it will be M. Here it will be M plus dm. Now, let us do summation of force along y direction equal to 0. So can you tell what will be the equation? Just tell so that you will learn it quickly.
dv by dx is equal to minus w.
dv by dx equal to minus w. So is this equation only?
Yes, sir.
Yeah. Now when you will take summation of movement, suppose this is point O, about O equal to 0, you will get dm by dx equal to v. Okay? And this is the positive sign convention I have taken for shear force and bending moment. Now come to this case. Now you can see this W, the direction is downward, means negative, because here also the direction was downward, so one minus will come. and the magnitude. Here also the direction is downward and the magnitude is W, which is constant throughout. Which now when you will correlate this with dV by dx, dV by dx means what? It will be the slope of the shear force diagram. So what we are getting from this equation, let us say this is 1, this is equation 2. You can say that the magnitude of the loading diagram will define the slope of the shear force diagram. So here, when you will come, it is minus W here. Minus means it is acting in the negative y direction downward. And here the load is constant throughout the span. Suppose the span length be L. So you can tell the shear force, the slope of the shear force diagram will be negative, as well as it will be constant because the loading diagram is also constant from this equation. So how the shear force diagram will look like? Can you tell now?
Straight lines.
Straight line, how? Will it be like this?
Yes, sir.
Yeah. Now tell the slope of this line. Is it positive or negative?
Negative, sir.
Negative. And what you got here? When W is acting downward, the magnitude of W is constant throughout and it is negative. So what the shear force, slope of the shear force diagram will be? It should suggest that the slope of the shear force diagram should be negative and the slope should be constant throughout. So at any point when you will see the slope is constant. Is it so?
Sir.
Now come to this second equation. Now it is showing the slope of the bending moment diagram will be equal to the shear force at that point. So now shear force diagram is this. For a part it is positive, for other part it is negative. Now you see at this point the shear force is positive maximum, and till this point, let this point be C, the shear force is positive but the value is decreasing. Here means from here what you can see, shear force is positive means the slope of the bending moment diagram will be positive, and with increase in span length, or means as we are proceeding from A to C, the value of the shear force is reducing, so the corresponding slope of the bending moment diagram should also reduce. From that is the conclusion we are making, right?
Yes, sir. Yes, sir.
So we know the bending moment diagram will be like this.
Yes, sir.
Now you see here you draw the tangent. Tangent will represent slope only. You take another point B and draw another tangent. Here you draw this tangent will be perfectly horizontal. So what you found? Here the slope was maximum. Here the slope reduces. Here the slope becomes 0, where the shear force is 0. And the slope everywhere is positive. Correct?
Yes, sir.
Now, for this part, when you will see the shear force, here the values are negative, and the negative value is going on increasing when we are moving towards the opposite support. So what you can infer? Please tell in your words so that you will understand.
Slope of the bending moment diagram will be decreasing,
Yeah.
and at the end it will become 0.
Slope of the bending moment diagram will be decreasing or increasing?
Decreasing, sir, because negative side it is increasing.
Take the mod value only. Say the mod value. Negative does not means that it is the magnitude wise it is increasing or decreasing. Negative or positive will show the slope. Now we will get like this, right?
Yes, sir. Yes, sir.
Yeah. So when you will draw a tangent here,
slope will be 0, increasing, sir.
The slope is increasing as the value of the shear force diagram is increasing, but the slope is negative.
The slope is negative, value magnitude is increasing.
Yeah. So you got it from these two equations, how we are means correlating the SFD and BMD from the loading diagram directly.
Yes, sir. Yes, sir.
Yeah. Now I will show you for this case. Now you can only say which one is correct. Now, see, here the load is acting downward and the slope of the load is constant, means the magnitude of the load is constant. Magnitude of the load is constant means the slope of the shear force diagram will be constant. Correct?
Yes, sir.
And negative means the slope will be negative. Till this point it is correct?
It's correct.
Got it? Now, what we got? Our shear force diagram. The slope of the shear force diagram will be like, suppose let us draw here for this section only, because throughout the section we have to take part by part section and we have to draw. So I am just showing it this part. Here it will come like this. Till this section I am showing. You check now. This, the loading diagram is negative. Load is acting negative and the magnitude of the load is constant. The magnitude of the load is constant means at any point, if you will draw, the slope is constant. Is it so?
Yes, sir.
Yeah. And the slope we got constant and the value that the W is negative. Negative means this slope is negative. At each point, the slope will be constant and it will be negative.
Negative. So
now, here, when we are coming to bending moment diagram, it is one order higher than shear force.
Yes, sir.
We have written in equation 2. Now see, here the shear force diagram is positive and it is gradually reducing when we are moving rightwards. So what will happen? If the magnitude is reducing, the slope should reduce. Correct?
Yes, sir.
And the value is positive, the slope should be positive. Means value is providing slope, means not value. Value means if it is positive or negative, that is providing us the slope. and how the value are increasing or reducing, that will provide the orientation of the slope. So for this case, if you will see, here the shear force is reducing. That means our value of the slope for the bending moment diagram should reduce as we are moving this in this direction. Correct?
Yes, sir.
And it is positive. So the slope will be positive or negative?
Positive.
Positive. So now our slope should increase. So 1 or 2, which one is correct?
Answer.
Yeah. Why?
The slope is decreasing, sir.
When you see here, the slope is almost vertical and gradually it is decreasing and becoming 0.
Yeah.
Here. So similarly, our shear force is also behaving like this, magnitude of the shear force. And since it is positive, so anywhere you draw a tangent, the slope is positive only. Correct?
Yes, sir.
So we can now eliminate this second plot. And what is the magnitude of this?
MF40Y.
Yeah, this is M by EI diagram. Now, when you will take a section here, let us say BB. It will be something like this. This is B. This is 40. This is 40. This will be suppose MXX. And this is BB. And here VXX. Now here VXX will be what? Sorry, VXX we are not interested in finding. We need to determine MXX at that section. It will be same, correct?
Yes, sir.
Yeah. So I am directly writing this minus 10x square plus 40x minus 40. So here put x equal to 2 meter, you will get 0, and x equal to 4 meter, you will get what will be this magnitude? 40 by EI, correct?
The 40 by H.
Yeah. Now for this section, from where should I take the x? From left support or right support?
Right supports.
Yeah, it will be easy if we will take from right support. Now, for this part, I am drawing it here only. This is x. This will be Vxx. And here it will be Mxx. Now tell me the Mxx equation here. It will be
NX squares.
20 x square by 2 minus 10 x square. Correct?
Yes, sir.
Yeah. So when you will put 0, it will be 0 here. And when you will put 2, it will be minus 40. This. So this is also negative. This is also negative. Now, this is M by EI diagram. Okay. This M by EI diagram, we will take it and put it in this conjugate beam. So let us do. So here we will have a roller. Just tell me if I am doing something wrong, because I am unable to see the previous figure. It was our correct conjugate beam, right?
Yes, sir.
Now, let us put like this. This. Now this M by EI diagram will be the loading diagram for our
Conjugate beam.
conjugate beam. Now what we need to determine? Deflection at point B. So delta B we need to determine for real beam. So what component we need to calculate for this conjugate beam?
Bending moments.
Bending
Bending
moment.
moment at B.
Yeah. Bending moment at B. So how to determine bending moment at B?
Area of the loading into 2/3 L.
Yeah. And
2/3 ka, sir. 3/4.
how the bending moment diagram is, sorry, loading diagram. M by EI diagram is something like this. This is A, this is B. Correct?
Yes, sir.
Yeah. And this is 2-degree parabola. So our N is 2.
Yes, sir.
So previous class only we have discussed, right?
Yes, sir.
If this is X bar, what is our formula? B
1/4.
upon N plus 2. Correct?
Yes, sir.
Where B is this 2 meter, means this width. So now it will be 2 by 2 plus 2 will be equal to 2 by 4. That means 1 by 2. Correct?
Yes, sir.
So this part will be how much? 2 minus 1 by 2. 3 by 2.
Oh, yes.
Now, tell me what about area? What was the formula?
H by N plus 1.
So what is B?
E is 2 meters.
H,
40 by EI. 40.
N.
2.
Yeah. So what is this value? 2 by 3. 80. 80 by 3.
Yes, sir.
Now we can directly write area into lever arm will be the bending moment. So
Yes, sir.
directly write 80 by 3 into what is the lever arm? 1 by 2 or 3 by 2?
3 by 2.
Yeah. So we are getting 40 by EI. So let us check if the options are matching or not. Which option? D?
Yes, sir.
Yeah. So is this problem clear to everyone?
Yes, sir.
Now, let us come to this problem. Here, let us read the problem. If 4 meter end segments have a moment of inertia I equal to 270 into 10 power 6 mm power 4. And the center portion has a moment of inertia just double, that is 2I. means this portion is slightly thicker as compared to the two side portions, such that if the moment of inertia is I here, then it will be 2I, where the values of I are 217 to 10 power 6 mm power 4. Now we need to determine the displacement at this midsection C, and it has been given the modulus of elasticity is 200 GPa. So we will do it using conjugate beam method. So first, tell me if the beam is symmetric or not, structure wise and loading wise, both.
Both are symmetric, sir.
Yeah. Then if this is AY and this is BY, tell me the reactions directly.
50 kilonewton, sir.
Yeah, 50 kilonewton, because the total vertical load is 100 kilonewton. So 50-50 will be divided to each of the joints. Now, we can directly draw a bending moment diagram now.
Yes, sir.
So, first we will draw bending moment diagram here. Next, we will draw M by EI diagram here. Now, let us cut a section here. Let this be AA. So, here MXX, if you will write, it will be 50x. Correct?
Yes, sir.
And that 50x, that equation is valid for x in between 0 to, tell me, what will be the upper limit?
4 meters.
Yeah. So at x equal to 0, it will be 0. At x equal to 4 meter, it will be 200. And it is linear because degree 1. So this is 200. Now, when we are taking the section here, BB, so I am writing it here because otherwise we will do mistake. This is 50 kilonewton till here. This is 30 kilonewton, and from here this is x, and here we are writing this is section BB, and we are interested in determining MXX. So here MXX will be 50 into x minus 30 into, this was 2 meters. Sorry, 4 meter, x minus 4. You got this equation, how it came?
Yes, sir.
Now upon simplifying, it will be 20x plus 120. So right, at x equal to 4 meter, what is the value? Tell me. At x equal to 6 meter, what is the value?
Equal to 200, sir. 200, 240.
So here something 240 will come. Now the beam is symmetric. The loading is also symmetric. Shear force will be anti-symmetric. Bending moment diagram will again be symmetric. So can we directly draw a symmetric bending moment diagram about this line?
Yes,
From
sir.
the center line. So this is 200, this is also 200, 0, 0, 240. Now divide it by EI. That is normalizing the bending moment with respect to flexural rigidity. So how it will look like? I am drawing, tell me if it is correct or not. Is it correct?
Yes, sir.
This is M by EI diagram. Now see the real beam. Real beam is simply supported. Correct?
Yes, sir.
So for simply supported beam, what will be its conjugate beam?
Same, sir. Simply support.
Same. Let me add slides. Now our beam is like this. Here it will be roller. Here it will be hinge. This is our conjugate beam. Now I am just imposing that load in this conjugate beam. Now Now we need to determine the displacement at the center. Center means this is center C of the beam. Now delta C at center for real beam, I am writing RB for real beam, will be equal to what?
Bending moment
at C for conjugate beam. Correct? Now we can directly do. For this, we need to determine the support reaction. This is point A. This is A and B. This is A and B. And you can directly do one thing. The complete M by EI diagram also is symmetric, and the beam is also symmetric structure wise and loading wise also. So we can directly write AY will be equal to BY will be equal to total load, means area under this M by EI diagram, area of M by EI diagram whole into 0.5. So let us determine the area one by one. Let this triangle be first one, this trapezium is second one, and this trapezium be third one, and this trapezium be fourth one. Now, if we will calculate the area of first and second and multiply it with 2, we will get the area of the total M by EI diagram. So I am doing area of 1 plus area of 2, then multiplying it by 2 such that we will get total area, then multiplying it by half. Then 2 and half are done. They will cancel out each other. So this area of 1 and area of 2 will directly provide the value of the support reactions. Now let us calculate area of 1. It will be half into length was 4 meter, height is 200 by EI plus area of 2. Trapezium area is half into sum of parallel sides, that will be 120 plus 100 by EI into the length will be 2 meter. Till now it is correct?
Yes, sir.
So we got these reactions as 620 by EI. So we can directly do now. It will be AY into the lever arm. What will be the lever arm?
6.
Then the major chunk will come again. We have to calculate the centroids for each and every shapes. Now for one, it is triangular. So we can directly write half into 200 by EI into 4 into, it will be 2 plus 1/3 of 4 minus, I am dividing this trapezium into a rectangle down and the triangle up. So for triangle, it will be half. This is 100, this is 120. So this height is 20 by EI. And the length is, this length is 2 meter. And that will be 1/3 of 2 minus the rectangle. Rectangle is nothing but 100 by EI into 2 will be the area and 2 by 2, 1 will be the lever. And so you can put AY to be 620 by EI. And when you will calculate, I have done it, you will get 6. Yeah, 6520 upon 3 EI. So now we know the value of E as 200 GPa and I as 270. So you put directly 6520 upon 3 into E. E 200 GPa into I is 270. So if we are just doing 200 into 270, it will come in the units of kilonewton meter square. So upon simplifying it, we will get 0.0402 meter. Yeah, that's it. So delta C equal to 40.25 mm. So is this problem clear to everyone?
Yes, sir.
Now let us come to question 3. Now in this question, we need to determine the slope of the beam at point A. Means here you need to determine theta A, where E of the beam is given as this and inertia is given as 8 into 10 power 6 mm power 4. Now, the same thing we need to first draw the M by EI diagram. See, this 50 kilonewton will try to rotate the beam clockwise. But the beam is at static equilibrium condition. So this 50 kilonewton will be resisted by a couple, and this couple will be generated by these two reaction forces, AY downward, and this AY will be downward and BY upward. How I know AY will be downward and BY upward? See, this 50 kilonewton will try to rotate it clockwise, and this AY and BY, when we are giving this position that AY is acting downward and BY is acting upward, it will be anti-clockwise. So both will balance out each other, keeping the entire beam in the state of equilibrium. And what will be the value? It will be 50 by 8. 50 by 8. So it will be 6.25 kilonewton. 6.25 kilonewton. So let us draw the bending moment diagram. 6.25 is acting downward, so minus 6.25, it will go like this, and a sudden jump of 50 kilonewton will happen here, and again it will merge here. And if all the ordinates are divided by EI or normalized with flexural rigidity, we will get the M by EI diagram. And this M by EI diagram, this is a simply supported beam, so its conjugate counterpart will also be a simply supported beam like this. So I have drawn it here only. And this M by EI diagram will look like this. And this will be the loading diagram for this conjugate beam. This will be 6.25 into 4 is 25, and normalized by EI will be 25 by EI, and this will be also 25 by EI. Now here we need to calculate this A reaction forces again. We have to calculate this. So, because we need to determine the slope at point A. So slope, that is theta A for real beam, theta A for real beam will be equal to AY. Is it so or not? AY, let us give it other name, AY prime. Otherwise, this AY and this AY you will get confused. Is the statement correct?
Yes, sir.
Yeah. Now let us determine AY prime directly. Now do summation of moment about point B prime. This is A prime, this is B prime, of I equal to 0. Let us take clockwise to be positive. So here it will be AY prime into 8 plus half into 25 by EI into 4 into what will be the lever arm?
4 plus 4 by 3.
Yeah. Then it will be minus 25 by EI into 4 into what will be the lever arm here?
2/3 4.
And that should be equal to 0. So let us do some simplification. 25 into 4 into 8 by 3 whole divided by 2. So this will be 400 upon 3i and minus of 25 by 4, 25 into 4 into 4 plus 4 by 4 into 4 plus 4 by 3 into 0. This will be 800 by 3i, and whole will be divided by 8. 400 by 3 minus 800 divided by 8. So it will be minus 50 upon 3i. So we got slope as minus 50 upon 3i. So let us put the value of ei is 200 into 8. I am getting minus 0.01 radian. So option C. So you got this question, right?
Yes, sir.
Yeah. Now the same problem here, they are asking to determine the maximum displacement. So the same problem we can just draw the M by EI diagram or the conjugate beam directly. This was 50 upon 3EI in the downward direction. Now we need to determine the maximum displacement. So maximum displacement for real beam will be equal to maximum bending moment for conjugate. So here we don't know where the maximum bending moment will occur. So as from mathematics we know the concept of maxima. Suppose we need to find M max, we can do a first derivative and make it equal to 0 to get the null points or the roots actually. So this dm by dx is what? Shear force, right? So we can directly write shear force equal to 0. So let this be section AA where we have to write the shear force. We can directly write minus 50 upon 3 EI plus half into 25 by 4 EI into x into this distance is x. Half into 25 by 4 is per meter into x will be the, that should be equal to 0. So what you will get minus 50 upon TI plus 25 by 8 EI into x square equal to 0. So upon simplifying it, you will get 25 by 8 EI into x square will be equal to 50 upon 3a. So EI will get cancelled. So x square will be 50 by 3 into 8 by 25. So 1, 2.
Four by root 3.
This is coming out to be 4 by root 3, right?
Yes, sir.
Means this square. So x is coming out to be 4 by root 3 meter. Now you just write bending moment M max at x equal to 4 by root 3. And when you will write the equation, it will be minus 50 by 3 EI into x plus this will be half into 25 by 4 EI into x into x into x by 3. Correct? Yeah. Just see the equation, if it is correct or not.
Sir, correct, sir.
Yeah. Then just substitute x as 4 by root 3 everywhere. So what will be the value? Let me check if I don't have the value. Let me calculate. We are getting minus 25.66 by EI. So minus 25.66 upon EI 200 into 8. Minus 0.01016 meter. 16 mm. So option D. Got it?
Yes, sir.
It clear?
Clear, sir.
Yeah. So let us move to next question. Yeah. You people just tell me how to do this question. In this question, we need to draw the conjugate beam only. So this is fixed end. So here which support will come?
3 ends.
3. This is internal hinge. So it will be?
Internal roller.
Yeah. And this is?
Hinge.
What it will become?
Internal hinge.
Yeah. And this is free end. It will be?
Fixed.
Yeah. So this will be the conjugate beam. No problem in this question, I hope.
Yes, sir.
Now, this is the question taken from R.C. Hibbeler book. Here we need to determine the maximum deflection again. And the properties of the beam material, modulus of elasticity is 200 GPa and inertia I is 60 into 10 power 6 mm power 4. So from here you will get EI. Now, the reactions are also given 2 kilonewton and 6 kilonewton. So we can directly draw the M by EI diagram. Let us draw it and check the beam. Beam is simply supported, so its conjugate beam also will be simply supported. So I have done its conjugate beam also, and we will directly superimpose the M by EI diagram above this span only. So when you will write mxx here, it will be 2 into x, and it is valid till 9 meter. So 2 into 0 is 0, 2 into 9 is 18. So it will be 18 by EI. And from this side, if you will write 6 into 0 is 0 for this point, and 6 into 3 is 18. So PMD will be something like this, or M by EI diagram for generality. So this will act as the loading or conjugate beam. So we need to determine the maximum deflection. For that, again we need to find the support reaction. Let this be AY. Let this be A prime, B prime, AY and BY. Now, we can determine summation of moment about point B of I equal to 0. We will do. So you will get AY into 12 minus half into 18 upon EI into 9 into 3 plus 1/3 of 9. Then minus half into 18 upon EI into 3 into 2/3 of 3 means 2 meter. And that should be equal to 0. Yeah. So AY will be equal to 9 into 9 into 6. 9 into 540 by 12. 55. This will be 45 by EI. And next equation, we can write summation of force along Y equal to 0 and vertically it is positive. So we can write AY plus BY minus, we can directly do half into 18 upon EI into it will be 12 meters equal to 0. And AY we know 45 by EI plus BY minus 12 9 So this we are getting 63 by EI. Now, again, for maximum deflection, M max is maximum deflection for conjugate beam. A maximum moment for conjugate beam will be delta max or real beam. So we need to determine M max for conjugate beam. So, but we don't know at which position it will come. So we can directly differentiate the equation of M with respect to X and we can make it 0. We'll get the root. So we have to first write MXX. Let us take the section here. Let this be MXX prime. Now, let us do MXX prime here. That will be 45 by EI into X minus half into 18 by 9 EI into X
Yes.
into X into X by 3. Correct? Just check if this is correct or not. And X I am telling this distance. So you can simplify 45x by EI minus, it will be 2 by 2 xs cube upon 3i. Till now it is okay. So just differentiate this. So you will get 45 by EI minus 3x square by 3EI will be equal to 0. So from here 3 will get cancelled out. So x square will be 45. So x will be under root 45. Now, what you need to determine maximum deflection. So you just put x here, you will get M max. So maximum bending moment for conjugate beam will be equal to maximum deflection for real beam, as I have written here. So M max you will get 45 into root 45 by EI minus root 45 cube by 3 EI. EI 200 into 60. So 45 root 45 by 200 into 60 minus root 45 root 45 by 3 into 200 into 60. So you will get 45 root 45 200 into 60 minus 45 root 45 by 3 into 200 into 60 into 1 into 1. I am getting this as 0.01677. 0.01677 meter means delta max is 0.01677 meter or 16 mm, around 16 mm. So you got it?
Yes, sir.
This question? This question is clear, right?
Yes, sir.
Yeah. Now, this is a cantilever beam. We need to determine slope and displacement at this free end. B for this steel beam having the following properties. Here I is, there is a mistake, 102 into 10 power 6 mm power. And the reactions are given directly 30 kilonewton and 90 kilonewton meter. So let us draw. So what is the name of this beam?
Cantilever.
So the conjugate will be like this. Correct or not?
Yes, sir. Yes, sir.
Yeah. So let us draw now the M by EI diagram directly and superimpose in this conjugate beam as loading. It will be, let us take sections from this right support or free end X. So in this 1 meter, 0 to 1 meter, there won't be any bending. So no bending movement. So we reached till here and there is no bending movement. Now, when you will take a section here, you will get minus 30 into, let us write it. MXX will be minus 30 into X minus 1. Is it correct?
Yes, sir.
Yeah. When you will put X is 1 meter, it will be 0 here. And when you will put X as 4 meter,
90.
4 meter, it will be 90. We got already.
Minus.
It is 90 minus. So it is straight line, negative, and directly let us superimpose in this conjugate beam. This is point A, this is point B, let us limit point C. Now, we need to determine theta B as well as delta B or real B. So theta B or real will be equal to what?
EY.
Shear force
Yes, sir. Shear force at B.
at B. So
So the
shear
reaction.
will be directly the reaction at B.
Yes, sir.
So the reaction will be directly the area, but in opposite direction.
Okay.
So it is 3 meter. This is 90 by EI. So the area of this M by EI diagram will be 90 by EI by 2 EI into 3. Is it correct?
Yes, sir.
270, it will be 135 by EI.
Yes, sir.
And the direction will be downward. So this will be 135 by EI. So 135 by what is E 200 into 102. 135 into 200 into 102. So I am getting 6.6176 into 10 power minus 3 radian. Please check the correction once, if it is correct or not. I don't have the solution for this.
Yes.
Is this correct? Till this point?
Yes, sir.
Yeah. Now we need to determine delta B, which will be equal to bending moment
At
at
B.
B for which beam?
Conjugate beams.
Conjugate. So bending moment you can write directly area into the lever arm. So we got the area 135 by EI into lever arm. What will be the lever arm?
1 plus 2.
So 135 into 1 plus 2 upon EI. So 135 into 3 will be how much?
405 by A.
405 by EI. So when you will divide by EI, it will be 200 into 102. Why I am doing 200 into 102? Are you getting or not?
I'm getting, sir. I'm getting.
Directly.
Hmm.
Because this will be in the unit of kilonewton meter.
Meter square. Meter.
And this I am making it meter square. This I am making it in the same unit such that it will be meter cube, sorry. Kilonewton meter cube, and I am dividing it with kilonewton meter square. This kilonewton meter square you can get by dividing this 200 with 102 directly. So I am doing it directly only. Okay.
Okay, sir.
So we are getting 0.019 meter, which is equal to 19 mm. So delta B is 19 mm. So we got theta B as 6.6 into 10 power minus 3 radian, and delta B as 19 mm. Let us move. Now the second method, that is called unit load method. During the deflection of trusses, we have used this concept of virtual work method. This unit load method is also same, and it is based on the concept of virtual work method only. So there we were doing for truss member and the joint deflection. So there we are getting like 1 into delta. This 1 unit was virtual force. You are applying at that joint into the real displacement, and we are writing it summation of K. That K force system was coming due to this 1 unit virtual load into PL by AE was the displacement of each members. So we are getting delta directly for truss members as summation of K PL by A. There we were doing summation because for truss members, when you will draw axial force diagram, throughout the member, the axial force diagram will be same. So when you will do the summation for the entire number or the number of members you have for the truss system, you will get the total displacement for the desired joint, and at that point in which direction you have applied the 1 unit virtual force. But when we are doing for frames or beams, for frames and beams, you will see the bending moment diagram is varying from each section to, means from one section, if the bending moment diagram is something, for other section it will be some other. It might be same, but in generalized case it may change depending upon the external loading condition. So here the external virtual work done will be same, just like in suppose for this case they are asking to determine the horizontal displacement at C. So I will give a unit horizontal force 1 unit. For this 1 unit, the actual displacement at these joints, let that be delta C. And that will be equal to, this is external virtual work done. And that should be equal to internal virtual work done. So when you are applying this 1 unit load, remove all those external load that is there in the structure and calculate this small m. This small m is due to
Unit load.
Is the movement, bending movement along the length due to this 1 unit actual force you are applying on any joint where you need the displacement. So you write this small m due to this 1 unit virtual force, and this will be d theta, and that will be integrated throughout the length of the member. So now d theta can be written as m into
By
n by ei into dx. So 1 into delta C, that is external virtual work done, will be integration over the entire length of the member m by ei into dx. You know now how this d theta becomes equal to m by ei into dx.
Yes, sir.
Yeah. So, and this is the internal virtual work done. So now, this is the concept for this unit load method. Now we will see this question. Now here, the flexural stiffness or rigidity of the L-shaped frame is EI throughout, means this is also EI. The flexural rigidity for this vertical member is also EI. We need to determine the horizontal displacement at this joint C. So I am applying this 1 unit. Let me draw the system once again. This is 1 unit. So I am dividing it and drawing the free body diagram for each and every member separately. This is 8 meter, this is C, this is B, this is also B, this is A. When you apply 1 unit here, is the member BC stable now? Static? It should be
Deflect, sir.
It should be static, but due to application of this 1 unit load, now is the member BC static or stable? No. So here this 1 unit will be reflected. Now check 1 and 1 will try to rotate the entire beam in clockwise manner. So one movement will come. This will have a magnitude of 8 units, and here also 8 it will come. Till this point it is clear?
Yes, sir.
Now, so when you are writing M1 for this 1, this for 2, we have to write M2. So I am taking X from this joint and X for this. Let this be X1 and let this be X2. So now, what will be M1? At any section XX from joint C.
Minus X. X.
minus x1, because this one unit will try to bend the beam inward, due to which in the outward reference section tension is generated, and that is hogging bending moment. So minus x1. When you will write for M2, what it will be?
8, sir. Minus 8.
For M2 at any section from this side. Minus 8, correct?
Yes, sir. Yes, sir.
Yeah. So we got this component. Now we need to determine that capital M due to external loads. Now, when you will see, this is due to original force system. This 1 kilonewton meter is here. It will generate one restraining moment here of 1 kilonewton meter, and that will be reflected here again 1 kilonewton meter to balance this joint. Now this is C, this is B, this is B, and here UDL is there, and this is 0.4 kilonewton per meter. And here also reactions will come. We don't know the reactions AY and MA to keep it in static equilibrium condition. Now, at any section, when we will write from this at a distance x, it will be capital M. What will be the value of capital M? It will be minus 1 throughout the member BC.
Sir.
And for this, if this is x2, for this, tell me, for this at any
Minus 1.
it will be minus 1 plus or minus?
Minus, sir.
Minus 0.4 x
Square.
by 2. Correct?
Yes, sir.
Minus 1 minus 0.2 x square. So now let us write. Where to write? I am writing here only. Delta 1 into delta C will be integration of BC. From 0 to 8 we are writing. M1 is minus x1 into minus 1 dx by EL. And the second one will be integrated from 0 to 10 here. What will be the small m1? Minus 8. And capital M1?
Minus 1 minus 0.2 x square.
And this is x2. I am writing as x2 only. By dx by EI. So what will be the integration values? I don't have to do. I am simplifying it. You just calculate. It will be 1 by EI can be taken common from each side. You can write x1 dx by 1 integration 0 to 8 plus minus from this bracket and minus from this bracket can be taken out. So it will combinedly become plus, and you can write 8 times 1 plus 0.2 x2 square and dx integration from 0 to 10.
10.
Can you do the integration? I am not calculating in further because this is the entire steps that needs to be followed to calculate the deflection delta C at joint C.
Okay, sir.
You got it, right?
Yes, sir.
Yeah, you can take this question down and you can try on yourself.
Okay, sir.
So, any doubt from today's section?
No doubt, sir.
Okay, I will send the YouTube link once generated. So that's it from today. Thank you.
Thank you, sir.
Okay, bye.